Today I'm going to present my paper titled Uncertainty-Driven Active Learning for Image Segmentation in Underwater Inspection. My name is Luisa Ribeiro Marnet. I am a PhD student at the REMARO project. That's a project financed by the Marie Curie grant. And in this project, the students are building different parts of an underwater autonomous vehicle using reliable artificial intelligence. And in my case, I am working with computer vision. My host institution is IVA in Denmark, and my university is the IT University of Copenhagen. My supervisors are Professor Andre, Dr. Yuri, and Dr. Stella. Thanks to deep learning models, computer vision has hugely advanced in the last decade. However, these models suffer from some problems. Between them, one of the problems is that they are data hungry. And when I say that they are data hungry, what I mean is that they need a lot of data for being trained. But let's check some images in this slide. These images are from a dataset called CumVid, that is a street view dataset. And as we can see, in many of these images, we have a lot of repetitive semantic information. So we have cars in all these images, we have the roads, the sky, we have buildings, we have traffic lights in many of the images. And if we check this other dataset, it is the same. This is a pipeline, an underwater pipeline dataset, and in all these images we have similar semantic information. So my question is, do we really need all the images in a dataset for training a model? Is it possible to train deep learning models with less data? And if it is possible, how to find the smallest amount of data to train a model? And with these questions, we have the goals of this paper. The main goal is, in the context of underwater images, to find a small subset of data to train a model with performance comparable to the performance achieved using the whole dataset. More specifically, we want to use active learning with Monte Carlo dropout to select a small subset of underwater pipeline images to train a segmentation deep learning model. As I said, we are going to be using active learning. Active learning is a family of methods that is used for selecting a small subset inside a dataset, and that this selected small subset can be used for training a model that achieves a performance comparable to the performance achieved by a model trained with the entire dataset. And for doing that, we need to calculate the uncertainty of the model for the predictions regarding each input. For that, we need to calculate the predictive uncertainty. The predictive uncertainty can be divided between epistemic uncertainty and aleatoric uncertainty. The epistemic uncertainty reflects the model's lack of knowledge, while the aleatoric uncertainty reflects the uncertainty of the data itself. Because here we want to select the inputs, in our case the images, about which the model doesn't have enough knowledge, so we can train the model for learning the pattern of this input that it doesn't know. We need to use the epistemic uncertainty. So we are going to use active learning and we are going to use the epistemic uncertainty. For calculating the epistemic uncertainty, we are going to use the Monte Carlo dropout. For explaining the MC dropout, let's check the image of this neural network. Let's say that in this neural network, in the first 3 layers of neurons, we have dropout layers. What dropout layers do is that they randomly drop out neurons of these layers with a certain probability. Usually, these layers are used during the training phase for preventing the overfitting. However, it can also be used for calculating the epistemic uncertainty during the inference phase. So, let's say that we have one input and we forward pass this input one time through the neural network. Because we have the dropout layers allowed, part of the neurons are going to be dropped out. And we have one output in the end. If we take this same input, in our case image, so if we take this same image and we input this image again, we forward pass this image again through the model, because all the neurons are going to be dropped out, since this drop is made in a randomly way, we are going to have possibly a different result. And then we are going to take the same image a third time and we are going to forward pass that image a third time through the model, finding a possible third different result. And again, and again. And we are going to input a same image t times. And for each one of these t times, we are going to have t possibly different results. If the model is well trained and if it has enough knowledge about this input, all the outputs are going to have a very close result. They are going to be very similar or maybe even equal. However, if the model is not well trained or if it doesn't have enough knowledge about this input, these outputs are going to be very different from each other. And using these outputs and the difference between these outputs, we can calculate the epistemic uncertainty. Different measures can be used for calculating the epistemic uncertainty, for example, entropy, mutual information, variation ratio, and total variance. In this case, we are using the mutual information that captures the model's confidence in its output. For briefly explaining how to calculate the mutual information is calculated with this equation on the top, where H is the entropy. So, for calculating this equation, first we are going to calculate the entropy for the average of all the outputs, for the outputs of all these forward passes for the same image. After that, we are going to calculate the entropy for each one of the outputs, for the output of each forward pass. And we are going to measure how different the entropy of each one of these outputs is from the entropy of the average of all outputs. And now we can use the Monte Carlo dropout in our active learning framework. In a first moment, our dataset is unlabeled and we are going to select p% initial images for labeling. We will label these p% initial images and use these images for training and validating the model. After that, with the trained model, we are going to use the Monte Carlo dropout for calculating the uncertainty of each one of these labeled images. And using this uncertainty, we are going to define a threshold. This threshold will be calculated based on the mean and in the standard deviation of the uncertainties previously calculated. Finally, we use this threshold, the threshold defined in the last step, for selecting new images for being labeled. What we are going to do is to take the model that was previously trained, and we are going to calculate the uncertainty of each one of the unlabeled images. And the images with an uncertainty above the threshold are going to be selected for being labeled. Using the previously labeled images and the new labeled images, we are going to retrain the model. And we will keep in this iteration of retraining the model and selecting new images for being labeled until we achieve a stop point. And this stop point, this stop criteria could be that we achieved the performance that's enough for our task, or it could be that we have a budget for labeling images and we used all this budget. It could also be that we are labeling more images, we are retraining the model, and the performance is not improving anymore. And using this framework, we are going to perform some experiments. The goal of these experiments is to compare a model trained with image selected through active learning with a model trained on randomly selected images. In our experiments, we are going to use two datasets, CANVID and Pipeline, that are the street view and the underwater pipeline datasets that I showed in the first slides. And we are going to train the deep learning model HyperSeg. HyperSeg is a segmentation model that is a state-of-the-art for the dataset CANVID. We are first going to train HyperSeg using active learning framework, so the framework that I've just explained, and later we are going to train a model, the same model, HyperSeg, using randomly selected images, and we are going to compare the results of both. For having a fair comparison, we are going to select the same amount of images randomly as the amount of images that we selected using active learning. In these graphs, we have some results. In the first column, we have the results using the CANVID dataset, and in the second column, we have the results using the pipeline dataset. And as I said, for both of them, we are using the HyperSeg model. In the x-axis, we have the percentage of data that was labeled. So in each one of these markers, we have a nil amount of images that were selected for being labeled, and the model was retrained using these new and previously selected images. In the first row, we have the performance of the trained models. This performance is calculated using the mean intersection over union. The mean intersection over union is calculated as the average of the intersection over union for each class. The intersection over union is calculated as the ratio of the intersection area to the union area of the ground truth mask and the mask predicted by the model for each class. And here we have in blue the performance of the model trained using active learning selection, and in green the performance of the model trained using random selection. In the bottom row, we have the difference between the performance of the two models. When the graph is filled with the blue color, the model trained with images selected based on active learning performed better than the model trained with randomly selected images. As we can see, in both experiments and in almost all iterations, the model trained with active learning performed better than the model trained with randomly selected images. Only in the end of the experiments, after the model already achieved a stable performance, for some iterations this is not true. It is interesting to observe that this difference between the performance of the model trained with images selected using active learning and the model trained with randomly selected images is much bigger for the pipeline experiment than for the CANVID experiment. Note that CANVID is a small dataset with about 500 images, while pipeline is a much bigger dataset with about 36,000 images. Also, the images inside the pipeline dataset vary a lot in quality, for example, because of the differences in illumination, blur, and color degradation. It makes it very difficult, very tricky to select the images of the pipeline dataset. And because of that, this is an ideal, it is a very good dataset for observing the benefits of using the active learning framework against the random selection. In this slide, we have some visual results for the experiment using the pipeline dataset. In these images, in the first column, we have the original image. In the second one, we have the ground truth or target. In the third column, the prediction performed by the model, so the outputs. And in the last column, the uncertainty or mutual information. In the table, we have in the first row the results for the model trained using active learning for the last iteration of the experiment. And in the bottom row, we have the result for the model trained using randomly selected images. In both of these experiments, in this last iteration, 12.5% of the images were used for training the models. One thing that's interesting for noticing here is that the class boulder and survey vehicle, that's the class with the least amount of images that contain this class, so only 15.5% of the images contain boulder and survey vehicle, is the class for each the difference between the model trained with active learning and the model trained with random selection was bigger. So for this class, the difference in the mean intersection over union was about 18%. Summarizing our conclusions, in our experiments, our framework was more effective for large datasets. So it was much more effective for the pipeline dataset than for the CANVID dataset. Using only 12.5% of the pipeline dataset, we achieved 67.5% of mean intersection over union for the model trained with active learning, while using the same amount of data, the model trained with randomly selected images achieved 61.4% of mean intersection over union. And finally, the class with higher mean intersection over union difference was the less represented in the dataset. That, as I said, was the class boulder and survey vehicle. Thank you very much for listening to my presentation.